And so it's now the top of the hour. I think we're ready to begin.
Okay. Well, welcome everybody to the virtual 2020 AOCS annual meeting and expo. And this is its live stream. So we welcome you to today's topic. I am Dr. Phil Kerr. I am the Chief Technology Officer of Prairie Aquatech here in the United States. And I'm very pleased to be able to be the host for today's presentation. Today, Dr. Sneh Bhandari is going to discuss methodologies that are used to determine very precise estimations of both protein quantity and nutritional quality for various dietary products. This could not be a more relevant and timely topic, and certainly appropriate to the veritable explosion of new protein-based offerings from all around the world, especially those coming from various plant sources. So for those that don't know him, Dr. Bhandari is a long-time and very active AOCS member and volunteer. He has worked in a number of areas to develop and validate and verify various methods in the food and the dietary supplement industries, especially including analyses for protein quality. Questions from the live stream discussion will be answered at the conclusion of the presentation, and we look forward to the interaction, even in a virtual format. With that, I'm now going to turn it over to Dr. Bhandari.
Hello, good afternoon, everyone. Myself, Sneh Bhandari, an independent consultant for last 3 months. Earlier, I was with the Mariu NutriSciences, Silica, as a R&D director. Thanks, Phil, for introduction, and thanks everyone for joining in this presentation. Thanks AOCS for organizing this meeting and providing me an opportunity to present on topic of nutrition labeling, which is, as Phil mentioned, important in current consumer emphasis on protein nutrition. I shall briefly provide a background about proteins and amino acids, the methods of analysis, health effects of different dietary proteins, and then involvement of protein quality in nutrition labeling. Proteins are part of almost all structural components of the body. They're critically involved in growth and development, all physiological and metabolic and specialty functions like reproduction, immunity, vision, blood clotting, endocrine, and name, and many, many more functions. Amino acids are proteins building block. They bond together in a peptide linkage to form proteins. The proteins' nutritional quality defined. Some amino acid can be made in the body, and that's how they're dispensable. Some amino acids can be made in the body, but not in enough conditions under all physiological and metabolic situations, and that's why they're called as conditional dispensable amino acids. And other amino acids are indispensable because body can't make them. And the requirement of the body's requirement has to be met by the dietary intake. These are the listed 9 amino acids in this slide. Some of the amino acids, particularly leucine, isoleucine, and valine, these essential amino acids have a branch chain, aliphatic side chain, and of course that's how they are referred as branch chain amino acid. They have a special functions in muscle. They promote muscle protein synthesis and also recovery of muscle following exercise damage and fatigue, not only in the athletes but also in older adults. The dietary proteins, of course, consist mainly of animal and plant sources. The both proteins, or most of the protein in the dietary, they do have the special features or features which can have health implications. The amino acids which are coming mainly from the red and the processed meat they are high, they have been found to be associated with the higher cardiovascular based disease mortalities. They are also high in saturated fatty acid and cholesterol. They lack dietary fiber and phytonutrients, which are often provided by plant foods. Plant foods, on the other hand, they are deficient in certain amino acid most of the time, or most of the plant foods are deficient in certain amino acid, maybe one or sometimes more than that. And that's why by themselves they are incomplete to meet the essential amino acid requirement of the body. There's also a possibility of risk transfer from animal food of antibiotic resistance. Health impact of the plant protein. Consumers are realizing more and more about the impact of the red and processed meat in the diet, particularly their bad health effects. And also they are appreciating the advantages of the plant foods in their lower risk of cardiovascular diseases and other diseases. At the same time, they're also realizing the superior environmental sustainability of the plant foods. That all is increasing a demand of the plant-based food, and that's what is creating increased demand of the alternative-based or plant-based foods. To meet this demand, food industry is developing more and new numbers of the plant and alternative protein-based foods to meet the consumer demands. These protein foods which industry is developing, they need to provide enough amount of quality proteins or good quality protein, and also to meet the nutritional demand of the essential amino acid, but also to appreciate or to realize the anticipated benefits of these new products. That brings in focus of the need of accurate and accepted methods of protein quantity and quality analysis. Protein quantity is often analyzed by its nitrogen analysis. So protein estimation is based on nitrogen analysis, most of the common standard methods. And the standard methods for these are often used are Caldor or combustion Dumas method. Nitrogen analyzed and then back calculated to protein based on nitrogen to protein conversion factor. On the other hand, quality of protein requires estimation of its indispensable amino acid content and also the protein's digestibility. This slide lists a series of various methods, Caldor methods. Caldor method is widely used for protein estimation based on nitrogen analysis. The methods have been optimized for certain matrices, and they use a specific nitrogen to protein conversion factor. This slide lists a series of methods, AOSC methods, which are optimized for certain matrices. Amino acid analysis requires the amino acid analysis of proteins require the release of amino acids from their proteins by hydrolysis. Often the hydrolysis is acid-based to release the amino acid, and then the released amino acid can be analyzed often by HPLC. There's a risk of acid hydrolysis to certain amino acids, particularly sulfur-hydryl amino acid, tryptophan, and also it leads to the conversion of glutamine to its respective acid, and similarly asparagine to aspartic acid. Resolution of these issues in the acid hydrolysis of protein is corrected by sulfhydryl amino acids are oxidized with agents like performic acid prior to the hydrolysis. Asparagine and aspartic acid, and similarly glutamine and glutamic acid are analyzed together as the sum of amine and the acid together for their estimation. Amino acids like tryptophan, which are also destroyed to or sensitive to acid hydrolysis, they are analyzed separately by a method involving either base hydrolysis or enzymatic hydrolysis. Amino acid hydrolysis method often use stabilizers for the amino acid, often phenol and some thiol derivatives. Amino acids are analyzed commonly by many HPLC methods. They are often analyzed by ion chromatography. They're resolved by ion chromatography and then detected by post-column derivatization using agents like ninhydrin, phenyl isothiocyanate, OPA, or like agents. Alternatively, amino acid can be analyzed by their derivatization before HPLC using agents like PITC, OPA, AQC, and then they are analyzed by reverse phase HPLC. And this is the case with some of the recently adopted method by OAC using AQC as a derivatizing pre-column agent. Amino acids in the HPLC, they are detected either by visible, UV, or fluorescence detection, depending on the way that the derivatization has been done. Tryptophan analysis is often performed separately by reverse phase HPLC, employing UV or fluorescence detection, and there are some AOC methods of this type. Protein quality is important in protein nutrition labeling. A food needs to meet a minimum threshold of its protein quality to qualify for declaration of its protein daily value. PDCAAS is a method of evaluation of protein nutritional quality for food meant over 1 year of ages. PDCAAS is protein digestibility corrected amino acid score. It requires analysis of indispensable amino acids in a food, and then it also requires the protein digestibility of the protein. So in essence, PDCAAS is relative indispensable amino acid amount corrected for its protein digestibility. Protein is declared on all the nutrition labels, which is a mandatory nutrition labeling, but percent DV of the protein required for the food of 1 to 3 year ages or foods where protein claims is made, and that requires an adjustment of the protein in the food by its nutritional quality, which is done by its PDCAAS value. So protein in food is multiplied by its PDCAAS value to provide quality adjusted amount of food in the protein in the food, which is then required for its percent daily value calculation. Protein efficiency ratio is a method of protein quality evaluation for infant foods. Canada's protein rating system is also based on PR, but it does allow PDCAAS to substitute PR in the case where PR value is not available. PDCAAS and amino acid score. PDCAAS requires estimation of protein and indispensable amino acid in the sample. Indispensable amino acid in the sample are calculated as milligram per gram of protein, and then they are compared against the reference pattern. Reference pattern adopted in PDCAAS is the indispensable amino acid requirement pattern for 2 to 5-year-old child approved by FAO/WHO in 1991. The relative least amount of indispensable amino acid in a food in comparison to the FAO pattern is a food's amino acid score or protein's amino acid score. This amino acid score is then adjusted for protein's digestibility by multiplication, and that is food's PDCAAS value or protein's PDCAAS value. Values over 1 are rounded to 1. Protein digestibility of food or protein which is required for PDCAAS calculation or estimation is often evaluated or estimated by rat fecal nitrogen balance method. Rat fecal nitrogen balance method is essentially, of course, a rat assay, and it is essentially a determination of percent of nitrogen intake, percent of nitrogen retained in the body of the ingested nitrogen. So ingested nitrogen, out of that, how much percent of nitrogen retained in the body is determinant of the protein digestibility of the food or the protein. Protein digestibility values of foods are available widely in the literature. Protein digestibility of a product can be calculated as a weighted average of protein digestibility of its ingredient and often applied for the protein purpose of the PDCAAS determination. An alternate assay of digestibility has been suggested in the FAO's newly recommended method of proteins nutrition evaluation method is DIAS, that is digestible indispensable amino acid score. That method uses pig ileal digestibility or amino acid digestibility assay rather than rat fecal balance method, which is employed by PDCAAS. In vitro assays of protein digestibility are available. No particular method has been recommended by FAO/WHO, but those are available, and Megazyme do offer a kit for in vitro assay of protein digestibility. This slide provides an example of PDCAAS calculation based on the values of indispensable amino acid of the sample, protein content of the sample. So what is derived from these calculations is each indispensable amino acid is calculated as milligram per gram of protein. That is compared against the reference pattern, FAO/WHO reference pattern for 2 to 5-year-old child, and the relative least amount of indispensable amino acid is the value of least amount of indispensable amino acid present in the food in relation to the pattern is considered food's amino acid score, which is in this case is 0.63 for the tryptophan. The amino acid score is then multiplied by protein digestibility, which is 0.86 in this case. So to obtain the PDCAAS value, 0.63, the protein, that is the amino acid score of the sample, is multiplied by its protein digestibility to get PDCAAS value of 0.54. Nutritionists and scientists have had a lot of concerns about the PDCAAS for many years. And some of these concerns have been addressed by newly recommended protein quality evaluation tool, DIAS, that is digestible indispensable amino acid score. That method has tried to address some of the shortfalls of the PDCAAS. DIAS uses the digestibility of each individual indispensable amino acid, where PDCAAS uses protein digestibility for PDCAAS calculation. The protein digestibility in case of PDCAAS is estimated by objective radical nitrogen balance method, where sampling for the DIAS method is done from pig ileal using a pig ileal method of amino acid digestibility assay. PDCAAS rounds values all 1 to 1, whereas DIAS recognizes values over 1. Both of the method, PDCAAS and DIAS, uses different amino acid reference pattern for relative comparison and to arrive at the amino acid score of the sample. Although this method has been recommended by FAO, WHO, and many nutritionists all over the world, but FDA has declined to accept this to replace PDCAAS in the lack of its database and also consensus about the use of its amino acid requirement pattern or reference pattern used to calculate amino acid score. This slide compares some of the literature value of the PDCAAS with corresponding DIAS values in case of some of the animal proteins. PDCAAS is presented in the red bars and DIAS is presented in the blue bars. As it can be seen, the PDCAAS for most of all these samples is lower than corresponding DIAS. That indicates somewhat underestimation of protein quality of animal protein sources by PDCAAS. Similarly, the next slide compares the literature values of PDCAAS and DIAS of some of the plant foods. PDCAAS values are presented in the red bars and the DIAS is presented in the blue bars. As you can see, in many of the plant foods, PDCAAS value, which is in the red column, is somewhat higher than the DIAS. That gives indication of somewhat overestimation in some plant foods of its protein quality. Nutrition labeling of proteins. It requires estimation of protein in the sample and then that is declared as per gram serving size to the nearest gram. Values under 0.5 gram can be declared to 0. Percent DD declaration of percent daily value declaration of protein is voluntary except in the foods of infants and children or if a protein claim is made in the food. It requires the estimation of quality corrected amount of protein, which is done by amount of protein multiplied by its PDCAAS value. Percent daily value of protein is corrected amount of protein in the food as percent of its daily reference value or it's a recommended daily intake or RDI value. Protein quality and nutrition labeling. As I mentioned earlier, protein quality is very important in its nutrition labeling. The PDCAAS score of a food of 4 years or older, if it is less than 20, it is labeled not a significant source of protein. Otherwise, it can be labeled with the protein's daily value, percent daily value. Similarly, PDCAAS of foods meant for children, if less than 40, is labeled not a significant source of protein. Otherwise, foods must be labeled with its percent daily value of protein. Food with a protein claim need to declare the percent daily value of protein. Infant foods should have a relative PR. When I say relative, it's a relative in terms of protein efficiency ratio of food in comparison to that of a standard, which is KC. Infant food should contain a relative PR of 40% or more and must declare its protein's percent daily value. Otherwise, food should be labeled not a significant source of protein. This slide provides an example of some of the old and new styles of the nutrition label. All the three labels which are presented here are declaring protein gram per serving size. But none of the samples or none of the labels are declaring protein's percent daily value, as indicated by the red circle. And more than so, the label provided in the red forms of both lines, it declares not a significant source of protein, although it has a 9 gram of protein per serving size. The reason being the protein of this food is an inferior quality in its nutritional aspect. And that's why it is labeling not a significant source of protein, although it has a significant amount of the unadjusted quality, unadjusted with respect to the quality. Protein nutritional labeling and common nutritional claims. Food making protein nutritional claim should contain enough amount of quality adjusted protein in relation to protein's DRV or daily reference value. To make a claim high, food should contain 20% or higher amount of quality adjusted protein in relation to its daily reference value. Similarly, food making a claim good source should contain 10 to 19% of its daily reference value in terms of quality adjusted protein. Food making claim of more protein should contain or should provide 10% of more quality adjusted protein of its daily reference value in comparison to an appropriate reference food of similar type. Other terms in place of high, good source, more, which are allowed in that category by law, those can be used for making claim. Protein spiking practice take advantage of protein estimation for nutrition labeling based on its nitrogen analysis. Food or supplement can be spiked with non-protein nitrogen substances like amino acids to inflate food's label value or declared protein value and possibly even make a claim. In these cases, protein estimation is not adjusted for food's non-protein nitrogen content. The sports nutrition industry has seen some of these types of practices and companies have been sued for these kind of allegations. One example of this type is high-tech pharmaceutical sued Allmax in late 1918 for declaration of inflated amount of protein on the label of one of their sports nutrition products. Review. A trend of high demand of healthy quality proteins from plant and other sources is continuing for some time. Nutrition labeling of food requires analysis of its protein and indispensable amino acids. Protein often estimated by its nitrogen analysis and back calculated to protein using specific nitrogen to protein conversion factors. Amino acids are analyzed by HPLC after the release from protein by hydrolysis. Nutritional quality of protein of foods over 1 year of age is determined by PDCAAS, employing amino acid score and protein digestibility in its calculation. It is required to declare protein's percent daily value. DIAS has been proposed by FAO-WHO in 2013 to address some of the shortfalls of PDCAAS, but has not been adopted yet in the lack of its database and consensus regarding its reference patterns. Amount of protein per serving size is declared in all nutritional labels. Protein's percent daily value need to be declared for foods of infants and children, and also for foods where protein claims are made. Otherwise, percent daily value of protein declaration is optional. Protein efficiency ratio evaluates the nutritional quality of protein foods or foods meant for infants. Canada's protein rating system is also PR based, but it does allow PDCAAS if no PR is available. And that concludes my presentation, and thanks a lot.
Thank you, Sneh. Phil is getting right back with us as his webcam comes on. There he is.
Hello, everybody. Well, thank you, Dr. Bhandari, for an excellent overview of this multifaceted topic. As we drill into the Q&As, let me ask one question of you. The challenges in your experience of measuring the protein quality of a, let's say, an ingredient in a food product versus, say, the final processed food product, and what impact does the processing conditions and the presence of other components in the final food product, what impact does that have on the analysis of protein content and protein quality?
Great, quite loaded questions. I try to answer in parts. First of all, the application of protein digestibility-corrected amino acid score in protein quality evaluation has been going pretty smoothly, particularly in the US, although there are a lot of drawbacks of PDCAAS pointed out by nutritionists all over the world. But as far as for the practical application, PDCAAS has been going pretty well. Reason being, it has a very good database of protein. It has a very good database for common foods. And as you suggested, yeah, if we have a new product developed, then a weighted average of its protein, of its PDCAAS or protein digestibility can be calculated based on the weighted average of its ingredient. And then based on the essential amino acid content of the protein, you can calculate PDCAAS of the newly developed protein, as long as the ingredients which are used in the product are common and their protein digestibility is available. As far as processing effect on the PDCAAS, there's a lot of literature about that, and very implied question, particularly in the current trend of the development of a lot of protein isolates and protein concentrate from different plant sources. The lot of plant protein may have toxins or some of the factors which may hinder in the availability of amino acids or other nutrients. The processing improves or destroys some of the components which may be anti-nutritional, and that's how the processing can impact the protein quality of the food by better utilization of the amino acids. Similarly, the release of amino acid in there is some literature available where the PDCAAS is known, it has been explored in the various processed food, and in some of the processed food, availability of amino acid is a little bit better than that of the uh, unprocessed. Problem is the database of the protein digestibility database which is available is limited. It is not available for all kind of ingredients or even the newly processed food. So very often a same protein digestibility factor will be used for the calculation of PDCAAS, although the food the food product which is where the PDCAAS is being calculated is somewhat differently processed. So there are a lot of implications of what you pointed out. Uh, it is known the PDCAAS can change with the processing, but how you determine the protein digestibility of newly available ingredient or newly processed ingredients or foods is somewhat difficult because protein digestibility assay, common assay or recommended assay is rat fecal nitrogen balance method, very difficult assay, a rat balance method. So in that way, this technique has some of these drawbacks, but that drawback will apply even to the newly suggested protein quality tool that is DIAS, that uses, instead of rat, it uses pig ileal model. Thanks.
Okay. So we have one of our audience members, we've translated their question from Spanish. So that gives you an indication of our international audience. And the question here is the quality of vegetable protein between animal sources and plant sources. Can you describe sort of the general differences between the two? I know it depends on the plant and it depends on the animal, and you had some good data in your presentation, but in general, could you describe the major differences between from a quality standpoint, an animal protein versus a plant protein?
Definitely, yeah. It's a good question and very applied from the perspective of what is going on in the industry now and increased consumer awareness. That two ways the animal proteins and the plant proteins differ. First, as I mentioned earlier, many of the plant proteins, they do lack in one or more of the essential amino acid, whereas most of the animal foods, they are complete in their essential amino acid supply. Or this, with respect to the requirement, most of the animal food or common animal food are able to supply or meet the requirement of essential amino acid or indispensable amino acid of the body. Whereas plant food, they lack in one or more of the indispensable amino acid. Said that, when I'm saying they're deficient by themselves, but you can mix two plant sources and complement the deficiency of each other, and that's how they can complete the amino acid need of the body if you complement them properly. Other way, the protein and the animal and plant proteins differ is the plant proteins are often layered or encapsulated by fiber or some layer which make them a little bit less available compared to the proteins coming from the animal sources. And so availability of the protein or the protein digestibility from the animal sources as well as the plant sources may be somewhat different. So there are two ways, there are two determining factors of the PDCAAS. One is its indispensable amino acid score or amount of indispensable amino acid present, and the other, the protein digestibility. In both the ways, the protein quality coming from animal sources is somewhat superior than that of the plant sources. But you can always complement the proteins from the plant sources to make them superiorly available. And other factor which make difference is if you process the the plant protein, by processing somewhat the availability of its protein with respect to release of amino acid is improved.
Okay, well, that's very relevant to another question that has come from the audience. And that question is, are whole food or processed food products evaluated or just estimated based on the ingredients used in the food via some sort of database? So you mentioned a couple of those within your presentation and even in your previous answer. So could you compare and contrast, say, a situation when you have say a minimally processed flour or even a vegetable or a fruit versus a pure ingredient, if you will. And then likewise, the challenges when you're in a formulated food versus an ingredient going into that formulated food, and then the roles that these underlying databases play in the ability to estimate what the protein quality scores would be in the case of a fully processed food.
Good question. Yeah. To answer this, as far as if the product for which PDCAAS need to be calculated, if it is like a standard food or conventional food, or if its ingredient are conventional and standard, then there's a very strong database of amino acid composition available in the literature, like from USDA and others. So many of the common foods, the amino acid composition is fairly established. On the other token, the protein digestibility database of most of the foods or most of the ingredient or standard or common ingredient do have a very good database of their protein digestibility. Based on that, based on the amino acid composition, either of the ingredient of a product, or if the product has a single source ingredient like just wheat flour, its known amino acid composition is fairly established. So based on that, and based on the protein digestibility of that, PDCAAS can be calculated. But if a product consists of various ingredients, then you can calculate its protein digestibility as a weighted average of its ingredient. And amino acid calculation in those kind of products, it may be there or maybe not. Some of the standard, even the finished product, amino acid composition is fairly established, and that may be available. Otherwise, depending on the processing or kind of thing, a relevant database may be looked for the ingredients and then manipulated amino acid composition can be calculated.
Okay, so for those in the audience who are interested in additional sources of information, thank you for sharing your email address. So we encourage those in the audience to reach out to you. If they did want to see where these ingredient databases were, or say they were curious about getting testing conducted on an ingredient that they're creating, or maybe a food product that they have created, and they needed to get access to either the swine ileal testing capability or particularly the rat protein digestibility capability, do you have any thoughts or suggestions of where audience members could go to get access to that information or those services?
As far as coming to the amino acid analysis, that is fairly standard method offered by many of the commercial testing labs like European or Mediu Nutrasciences, and likewise many of the testing labs do offer that kind of service. As far as coming to protein digestibility assay, particularly by recommended, the one which is recommended by FAO WHO, the RAG bioassay, that is a little bit difficult proposition. There are not many places which offer the protein digestibility assay. So it is often calculated based on its ingredient composition and the literature values. Some of the academic institutes which are doing the research, they may be able to offer. And things make a little bit more complicated in this sense is that WHO has suggested a new tool of protein quality evaluation that is DIAS, and that tool has not established its amino acid digestibility values for common foods yet. So there's a lot of research going on, and funds have been provided by European Union and other agencies to develop that database. So many labs are working to develop the amino acid digestibility values for common foods required for DIAS calculation. But there are some academic institutes which, if any of the audience members require additional information, they can send me email, and definitely I can provide additional information to them.
Well, on behalf of the audience and the AOCS, Dr. Bhandari, we appreciate the time and effort in both putting together the presentation and communicating it here today. And if we're not seeing any additional questions at this time, please reach out to Sneh, and if you have additional questions in the future, this would be a great resource for you as you go down the path with your commercialization of your future protein-enriched foods. So again, thanks for the time, and thanks for everyone's participation in today's live session. And we ask you to continue your participation in the virtual meeting. It's going quite well. So thanks for your time and effort all. And with that,
thanks a lot, everyone.